Well, hello and welcome to today's lecture. So we are on double integrals using polar coordinates. Polar coordinates. So let us begin by asking this question. Suppose you have an ice cream cone. Ice cream cone. And on top of it, we have this ice cream. And you're wondering how much ice cream you have in this ice cream cone. Suppose your cone is given by z equals to square root of x squared plus y squared, and on top you have a hemisphere that is given by z equals to square root of 2 minus x squared minus y squared. How much ice cream you have in your ice cream cone? This question can be answered using polar coordinates. First of all, let's review a little bit. Review. Well, suppose you have your point x and y, and then for this point, suppose this point forms theta, angle theta with positive side of x-axis. X-axis. Okay, very well. So of course you can form r. R is equal to square root of x squared plus y squared, and at the same time you can use tangent to define theta. Theta is equal to inverse tangent y over x. So remember that this point in rectangular coordinates can be defined by r and theta in polar form. Remember that x is defined as r cosine theta and y is defined as r sine theta. Very well. When do we use polar coordinates when we are actually evaluating double integrals? So let me erase all of these for you. So when a region is actually a circle, it's cardioid, or if you have rose petal, or if you have x squared plus y squared in your integrand, you can use polar coordinates. You can use polar coordinates in many cases. For example, if a region R is given as a circle, or a cardioid, or other ones like rose petal, or if you have the integrand including x squared plus y squared, it's easier to use polar coordinates to calculate or evaluate your double integral. Very well, let's begin. So the formula is double integral of f of r cosine theta r sine theta r dr d theta with the condition that r is in between a and b and alpha is the lower limit of your theta and beta is the upper limit of your theta. So here you have a continuous function. F is continuous. R is in between A and B, and theta is in between alpha and beta, and we have this condition that beta minus alpha is in between 0 and 2 pi to make sure we do not turn around the origin too many times. So where does this formula come from? I'm saying that this formula is the same as double integral of f of x and y dA over region R. So suppose you have your region R, which was in actually rectangular coordinates, and you write this as a set of points, R and theta, in polar form, such that R is in between A and B, and theta is in between alpha, beta. Okay, let's try to imagine what's going on here, go over some details. So where we got r d theta from. Okay, perfect. So I have polar rectangle here, and I'm just having one piece of this region. So help me to visualize what's going on to explain this formula a little bit better for you. Okay, here we have R equals to B, and suppose this is R equals to B. We can write A and B here. Okay, my theta alpha and my theta beta. So suppose this is the region that you have. This is your R. Okay. So it's very similar to what we did before using double Riemann sums. What I'm going to do, I'm going to just slice this region up. So I'm going to take this region, R, and slice it up. Okay. There we go. So like before, I'm trying to get some small pieces out of this slice piece. So take a look at this. Suppose I'm taking just this piece here. I'm trying to calculate the area of this piece. Of this little piece here, I need some information. First of all, I'm slicing up A and B into M subintervals. So remember that my R is in between A and B, so I get subintervals R I minus 1 and R I with equal with delta R, which is equal to B minus A divided by M. And at the same time, since my theta is sandwiched between alpha and beta, I'm taking alpha and beta interval and slice it into n subintervals. So let me use a different index, theta j minus 1 and theta j, and delta theta is equal to beta minus alpha divided by n slices. So let us take a look at this. I'm just trying to take this piece and visualize it better for you. So what I did, I just slice this guy up. My A, my B, my theta. Okay, so I'm taking just this little piece here. The information that we have for this little piece are as follows. Very well. So here you have theta j and theta j minus 1. And here we have, for example, let me use a different color. Ri minus 1 to Ri. Okay. So what is our goal? Our goal to actually calculate this little area here. So let us call it Rij. So this is called Rij, which is a small polar rectangle. So small polar rectangle. Small polar rectangle. Very well. Now, what I'm going to do, I'm going to define this small polar rectangle this way. I'm saying that Rij is equal to the collection of R, and thetas such that, so my R ranges between Ri minus 1, Ri, and my theta ranges between theta j minus 1 and theta. So this little slice here is actually a collection of R and thetas with the condition. So recall that from algebra, from pre-calculus, that the slice, if you have the slice of a sector of a central circle, if you have this here, if the area, the radius is given, you have your theta, then the area is equal to a half r squared times theta. Okay. This is the area. So the area of this little piece is equal to the half delta theta. So we get the half delta theta R, but your R is actually changing. So we have to take these two into account. Ri squared minus a half delta theta R minus 1, I minus 1 squared. So note that the difference between these two, delta theta j minus theta j minus 1, this is the measurement on this side, and on this side we have the difference between Ri and Ri minus 1. So here and Ri minus Ri minus 1. So why we are writing it this way, not just taking the delta between these two, why is that? Because as I mentioned here, this is the area of this complete sector. What are we going to do? We're going to just take the difference between these two areas. So here you have your Ri minus 1 and Ri, and so to find this little area here, they have to subtract this small area from this big area. That's why they have to write it this way. This is the area of the complete sector and this is the area of the smaller sector. There you go. Excellent. So this is what we have so far. We can simplify this and we get a half delta theta Ri squared minus Ri minus 1 squared. This can be written as a half delta theta Ri minus Ri minus 1 times Ri plus Ri minus 1. Very well. Now we need a little bit of definition because we want to write it in the format that it actually makes more sense for us. So what I'm going to do, I'm going to erase this one. I'm going to erase this one. And I'm going to write a little bit of new definition. I'm going to try to define the center of this little part of the region here. So I'm going to tell you that, well, the center of Rij is, let's define it this way. Let's say that, hey, this is equal to the set of all R and J's, R and Theta's, remember that we are in polar form, such that R is in between Ri minus 1 and Ri, and theta is in between theta j minus 1 and theta j. Okay, now I'm going to take the midpoints and define it this way. I'm going to tell you that, hey, I have Ri star, which is defined as Ri plus Ri minus 1 divided by 2, and I'm going to define theta j star, which is theta j plus theta j minus 1 divided by 2. It helps me to actually focus on the center of this region and take the integral. So note that here you have Ri minus 1, which is actually delta R. That's how we define delta R. And a half Ri plus Ri minus 1 is going to be Ri star divided by 2. This is my Ri star. There you go. So far, so good. So let's write this piece of information that we have here. So here you have, let me see, the area of Rij is defined as delta theta, delta R, and here we have Ri star. And we define Ri star here. Let me erase this part for you. Now you see, I have my area, and now I'm going to take the double Riemann sum. So first of all, the rectangular coordinates are in the form of x and y, and the polar coordinates are going to be in the form of Ri star cosine theta j star and Ri star sine theta j star. Okay, perfect. Now, if we take the double Riemann sum over j over I, and for our function is function x and y, I'm going to convert all of them into polar coordinates, polar format. Ri star cosine theta j star, comma Ri star sine theta j star. Okay? So the area of this little piece is actually Ri star delta theta delta R. Okay, you're finding these little volumes here, and now if you take the Riemann sum and take the limit, you get actually the double integral of f of r cosine theta, r sine theta. This r comes from here, r d theta d. And suppose your r ranges between a and b, and your theta alpha to beta, and with these conditions. That's how we get this r. It's very important. Students usually forget to write down this r when they actually transform their integral into polar form. They usually forget to write r d r d theta. But make sure you have your r, because it comes from finding the area of those little regions.